Hey guys, this is the third video that relates to the second half of chapter 14. I'm picking up on slide 22 of the PowerPoint. So here we go. So I have a given reaction. I have CH3Br. It's reacting with sodium hydroxide. Sodium's a spectator. But so CH3Br reacts with hydroxide. Basically, this is what's called a substitution reaction in organic chemistry. You'll see this reaction if you get to organic chemistry next semester. But essentially what happens is the hydroxide comes in, the bromide leaves, they swap places, and I get these products. Okay? If we study this reaction, we do the experiments that we talked about in part one, like the method of initial rates, we could determine that the rate law for this reaction, the rate equals K times the methyl bromide to the first power times hydroxide to the first power. Okay? That is the rate law for this reaction. So both reactants are first order. Okay, now what does that mean? It means that either one of them, if I double the concentration of methyl bromide, the reaction will go twice as fast. If I double the concentration of hydroxide, the reaction will go twice as fast. Because when things are first order, then the rate is directly proportional to whatever I do to the concentration. Okay? Now, another similar reaction. This molecule is very similar to that one. It's just a little bit bigger. It's got more stuff on it. But it's the reaction, again, I'm going to add hydroxide, which is going to jump in and kick out the bromide. So this is also a substitution reaction. But when we do the experiments, we actually find out the rate law for this one is different from that one. On the first reaction, I found out that both reactants were first order. On this reaction, actually find out that the organic molecule, which would be tert-butyl bromide, it's first order in the mechanism, but the hydroxide doesn't even show up in the rate law. And if I don't see it in the rate law, that means it must be zero order. And if it's zero order, that means that hydroxide, if I increase the concentration of hydroxide, it has no effect on the rate of this reaction. Why? Why would a molecule, if it's one of the reactants, why wouldn't, if I put more hydroxide in there, it seems like it'd give me more collisions, so why wouldn't the reaction speed up? Okay? Well, the answer to that, which is a really important question in organic chemistry, the only way we can explain why hydroxide matters up here, but it doesn't matter down here, is that the reactions must be happening in a different way. There's something significantly different between these two reactions, even though they look very similar on the surface, okay? And in organic chemistry, we spend most of our time in that class trying to understand how organic reactions happen. Why do some reactions work and other reactions don't, okay? So we need to get down into the nuts and bolts. So, question, why does hydroxide affect the rate of the first reaction, but it does not affect the second one, okay? Next slide. So if we look at the first reaction and we study it, what we find is methyl bromide, which is the CH3Br from the first reaction on the previous slide, it's a pretty small molecule. The carbon, all it has around it has bromine on one side, and then the three hydrogens, they're pretty small. They don't take up a lot of space. So basically, if the hydroxide wants to attack the carbon, there's plenty of room around the carbon for the hydroxide to like sneak in there and attack it, and basically the lone pair on the oxygen can extend out and form a bond with carbon, and when that bond forms, I know that carbon can only be part of 4 bonds at a time. So if carbon forms a new bond with the hydroxide, then it has to break another bond. So carbon says, hey, I would rather bond with hydroxide, so he kind of kicks bromine out. And since he's getting a new bond from hydroxide, bromine gets to leave and take the electrons with him. So that bond, when it breaks, he just takes those with him. And what happens is I make a new molecule, methyl alcohol is what it's called. And then actually I should have plus Br minus, because the Br minus just leaves by himself and he goes on and does something else, right? So in that reaction, it happens in one step. The hydroxide attacks and the bromine leaves at the same time. And if it happens at the same time, that means that both molecules are involved, the methyl bromide and the hydroxide. And if I increase the concentration of either one of them, it's going to speed it up. So that's why, since both molecules take part in this is a single step reaction, so we call it an elementary reaction, or we use that term. Both molecules are involved, so both of them affect the rate. Okay? That's why both of them ended up being first order in that reaction. All right, so now, if I look at the next reaction. This one has a lot more stuff going on, but essentially if I look at my initial molecule right here, the tert-butyl bromide, the carbon now has 3 CH3s around it, and each carbon, the hydrogens are all sticking out. It's a lot more crowded, okay? And again, in organic, you'll learn more about this stuff, but when it's more crowded, that means the hydroxide that I want to kind of come in and attack, it can't get in there because there's too much stuff in the way, okay? So it can't really get in there and attack, so it has to wait. The hydroxide just has to wait. What has to happen first, this molecule is actually a little bit unstable. The bromine actually doesn't mind kind of breaking off and going to do its own thing. So every once in a while, the bromine's just going to break off, take the electrons, and pull away, and it leaves carbon with only 3 bonds. And since bromine took the electrons, it leaves carbon with a positive charge. So essentially, a neutral, stable molecule just spontaneously breaks apart. Now, why does it do that? Well, remember, if molecules are all moving around, when they bump into each other, just think about like you're driving your car, and occasionally like you bump into a curb, or you bump into, I don't know, a wall or whatever. Even by yourself, there's a certain likelihood that you might get in a little bit of a fender bender, okay? It's more likely if 2 cars crash into each other. That happens more. That's what happens up here. But sometimes one molecule can bump into something and break all by itself, okay? So that's what's happening here. The first step here, we just have to sit and wait for the bromine to break off. Once it breaks off, this carbon, which was tetrahedral and had stuff all around it, once I break one off, this carbon with only 3 bonds around it is going to be trigonal planar. And if it's trigonal planar, that means everything's flat in one plane. So then that allows a hydroxide or a water molecule, it can depend, but one of them is going to attack and then form my product, which is the alcohol it's trying to get to, okay? Now, but the key difference here is that I described 2 different steps. The first step only involved this reactant. It has to spontaneously just break apart. And if that doesn't happen very well, that's going to be the slow part of the reaction. We have to wait for the molecule to break apart. So that's the slow step. Once we form that positive charge, the hydroxide is going to jump in there because he's attracted, the negative charge of the hydroxide is attracted to the positive charge of the carbon. So the second step is going to happen fast. Okay? Now, if we're studying kinetics, we already said earlier, the slow step is the one that controls the rate. And if the slow step only involves this molecule, then that's the only one that's going to be in the rate law. Okay? So that's why the rate law for this reaction and the rate law for this reaction are so different from each other. Okay? Now, we mentioned the term a couple slides ago, molecularity. Basically, when we're looking at a step, just one step of a mechanism, if that step only has one reactant molecule, we call that step unimolecular. Okay? Now, if a step involves 2 molecules, like A plus B, if 2 molecules have to collide with each other, it's bimolecular. Now, bimolecular, it could be 2 molecules that are different, A and B, or it could be 2 of the same, A plus A, which we usually write on one side, we say 2A yield something. When I say it's 2 molecules of A, 2A, that really means A plus A. There's 2 of them, right? So the way it's written can change. But if there's either 2 A molecules or an A and a B molecule, that's called bimolecular. And then finally, you can have three molecules that collide. It could be three of the same, A plus A plus A, which would be written just 3A in a reaction. Or it could be two A molecules and a B molecule. Or it could be A plus B plus C, right? But in any case, if there are three molecules that have to collide with each other, that's called termolecular. Now that's as high as we go, okay? Why don't we have four molecules colliding? Well, if we think about it, we have to think about in a collision, a elementary step has to be a singular event, okay? So you have to think about in a car crash, how often will one car just crash into the curb or a wall or something? Like, well, okay, that happens sometimes. Unimolecular reactions are somewhat common. They do happen sometimes. Most reactions are bimolecular. Two molecules crash into each other, just like a car crash. Most car crashes involve two cars. Okay? Now, what about three? Three molecules or three cars crashing into each other is actually pretty rare because usually they don't all crash into each other at the same time. If two cars crash into each other and then later a third car crashes into those, that's actually two separate steps. That's a bimolecular reaction followed by another one coming in a later step. So those aren't elementary steps. That's not one elementary step, okay? Very rarely will three cars crash into each other all at once. It can happen, but it's rare. So most reactions are going to be unimolecular or bimolecular. You'll occasionally get a termolecular, but you're not going to get any more than that. It's almost impossible for four molecules or five molecules to simultaneously all crash into each other and give us a singular molecular event, which is what we're talking about. Okay? Now, for each one of those, if for that step, we should be able to write a rate law. So if it's unimolecular, the rate law, if there's only one molecule involved, the rate will equal K times that molecule. If it's bimolecular, if it's A and B, well, there's one of each. So when I write the rate law, my coefficient in front becomes my exponent. So this rate law, in the slow step, or the step we're looking at, the rate of this reaction would be K times A to the first times B to the first, because in that step, there is a single A molecule and a single B molecule. So those coefficients become my exponents. Now, the one above it, A plus A, I would normally write that in a reaction as 2A. So that 2 becomes the exponent. The rate equals K times A squared. Okay? That squared means that there are two A molecules involved in this step. All right? And then termolecular, again, it matches up with how many of each molecule there are. Okay, now why is that? Like, why in the first one is A first order? Well, just think about if I have just A molecules flying around and occasionally one bumps into the wall and breaks or whatever. If I double the concentration, then I'm going to get twice as many collisions. So doubling the concentration gives twice as many collisions. That's going to be a direct direct relationship between the concentration of molecules and the rate. So that's what the first order rate law looks like. Now the next one, if A and A have to collide with each other, well, if you double the concentration, that means that this A molecule, there's going to be twice as many of them, but also there's going to be twice as many of the other A molecule. Like A is changing on both sides. So doubling the concentration of A doubles this one and doubles this one, which is why the reaction would go up by a factor of 4. If there are two A molecules involved, A is second order. So then if I double this value and square it, the rate would go up by a factor of 4. Okay? So mathematically, all this stuff is related. What you need to take from this is whatever the coefficient is, if we have an elementary step of a reaction, then you can take the coefficient and make it the order. If you don't know if a reaction is elementary or not, then you can't do that. All right, so when we write a mechanism, which a warning here, this is important. You will not have to come up with your own mechanisms in this class. We will always give you the mechanism. You're just going to have to be able to look at it, evaluate whether it's a good mechanism or not, and then use it as needed. Okay? But you don't have to develop the mechanism on your own. When you go to organic chemistry, you will, but not in 1212. Okay? So, when we are given a mechanism, and if we want to decide, is it reasonable? Is it plausible? Like, is it possible that it's a true mechanism? Well, number one, we need to be able to look at each step, and we should be able to write a rate law that applies to each one, which we've learned enough, so you should be able to do that. But you have to have a balanced equation for each step. Okay? Now, when we do that, whichever step is the slow step, if you write out the rate law, which the predicted rate law is going to come from the slow step. If you write that rate law out, it has to agree with the experimental results. The experimental results, if you go into the lab and you do the method of initial rates, and you find out that like reactant A is first order and reactant B is second order, if your mechanism disagrees with that, then your mechanism is wrong. Okay? The experimental results are reliable. When we do the experiment, we can prove conclusively whether a reactant is zero order or first order or second order. If you write a mechanism that disagrees with the experiment, then your mechanism is wrong. You need to scratch it out and come up with another mechanism. Again, you don't have to do that, but if we're evaluating mechanisms, that's what we're looking for. Your mechanism has to agree with the experimental results. Okay? Now, next thing, Hess's law, if you take all the steps of a mechanism, you should be able to add them all together, cancel things out on both sides, and get to the overall reaction. If you can't get the overall reaction from the steps that you wrote, then again, you messed up, and your mechanism is no good. Okay? So the individual steps have to add up to give the overall reaction. And you have to have the right stoichiometry, which means the coefficients of the equation should match up. Every step has to be balanced. Any intermediates that are made during the process have to be used later. You can't have any extra molecules floating around that aren't supposed to be there. And if we have a catalyst, if we use it, we got to bring it back. Again, we'll talk about that later. All right, that's a good place to cut off. We'll finish up in the next video.